Have you ever thought about where all the data from your cat videos, endless selfies, and late-night food delivery orders actually goes? It's all stored in massive data centers, sprawling complexes of servers that consume enormous amounts of energy and take up a ton of physical space. And here's the kicker, we're creating more data than ever before. It's estimated that by 2025, the world will be generating 463 exabytes of data each day. That's like streaming over 200 million movies in high definition every single day. Clearly, our current methods of data storage, like hard drives and flash memory, are struggling to keep up. They have limited lifespans, are vulnerable to damage, and require constant power. But what if there was a better way? What if we could store all the world's information in a space no bigger than a showbox? It sounds like science fiction, but the solution might be hiding inside every living thing on this planet, DNA. That's right, the same molecule that holds the genetic blueprint for you, me. And every other organism could be the future of data storage. DNA, or deoxyribonucleic acid, is nature's ultimate hard drive. It's been storing vast amounts of biological information for billions of years, flawlessly preserving the instructions for life. So how can we tap into this incredible power? The basic idea is to translate the binary code of digital data, the ones and zeros that make up everything from a text message to a blockbuster movie, into the chemical language of DNA. Digital data is represented by just the digits 0 and 1. DNA has a slightly more complex alphabet, consisting of 4 chemical bases: adenine, guanine, cytosine, and thymine, which we usually just call a G, C, and T. Scientists have developed methods to assign binary sequences to these DNA bases. For example, we could say 00 represents A, 01 represents C, 10 represents G, and 11 represents T. Using this system, any digital file can be converted into a unique sequence of DNA bases. Once we have this DNA sequence translated from our digital file, the next step is to actually create it. This is done through a process called DNA synthesis. Think of it like a highly specialized 3D printer, but instead of plastic, it's building molecules one base at a time. This process creates synthetic DNA strands that are identical to our target sequence. After synthesis, we have a tiny, almost invisible pellet of whitish powder. This powder is the DNA, and it contains all our data. To put its density into perspective, a single gram of DNA can theoretically store over 200 million gigabytes of information. All the movies ever created could be stored on something smaller than a sugar cube. So we've stored our data. Now, how do we get it back? This is where DNA sequencing comes in. We take our DNA sample and run it through a sequencing machine. This machine reads the order of the A, C, G, and T bases along the DNA strands. The resulting sequence is then fed into a computer, which uses the original encoding scheme to translate it back into the binary ones and zeros. And just like that, your digital file is perfectly reconstructed, ready to be viewed or used again. It's like reading a book written in a 4-letter alphabet. The advantages of DNA data storage are mind-boggling. First, let's talk about density. As I mentioned, it's incredibly compact. Forget sprawling data centers. We could store the entire internet's worth of information in a single room. This would drastically reduce the physical footprint of our global data infrastructure. Second, durability. When stored under the right conditions, cool, dry, and dark, DNA can last for an incredibly long time. We've successfully sequenced DNA from fossils that are hundreds of thousands of years old. Compare that to a hard drive, which might last a decade if you're lucky, or even archival quality magnetic tape, which degrades after about 30 years. DNA offers a way to preserve our collective knowledge and culture for millennia. Imagine future civilizations being able to access our digital archives, our art, our science, our history, long after our current technology has crumbled to dust. Furthermore, DNA storage is incredibly energy efficient for long-term archiving. While the initial writing and reading processes require energy, once the DNA is synthesized, It needs zero power to maintain the stored information. This is a huge contrast to current data centers, which are often called server farms, and consume about 1% of the world as total electricity, a number that's constantly growing. By switching to DNA for cold storage data that we need to keep but don't access frequently, we could significantly reduce our global energy consumption. Of course, this technology isn't quite ready for your next smartphone. There are still some major hurdles to overcome. The biggest challenges right now are cost and speed. Synthesizing and sequencing DNA is currently a slow and expensive process. Writing a few megabytes of data can take hours and costs thousands of dollars. It's nowhere near the speed and affordability of your USB flash drive. However, the costs of both synthesis and sequencing have been plummeting over the past decades, following a trend even faster than Moore's law, which famously predicted the exponential growth of computing power. As the technology continues to improve and scale up, we can expect costs to drop dramatically. Another challenge is developing efficient methods for random access. With a hard drive, you can instantly jump to any specific file. With DNA storage, it is currently more like sifting through a giant pile of microscopic scrolls to find the one you want. Researchers are working on clever solutions, like using PCR, the same technology used in COVID tests to selectively amplify and read only the DNA strands that contain the desired file, essentially creating a molecular search function. They're also developing molecular primers that act like file labels, making it easier to locate specific data within the pool of DNA. So what does the future look like? Well, you probably won't be backing up your photos to a DNA drive next year. The potential applications are vast. Archival institutions like national libraries and museums could use DNA to preserve priceless cultural heritage for tens of thousands of years. Large corporations and governments could use it for secure, long-term data archiving. Imagine a seed bank for data, where the most important information of our civilization is stored safely, impervious to power outages, magnetic fields, and the passage of time. Researchers at Microsoft's Project Silica are already exploring similar concepts using glass, but DNA offers even greater density and longevity. Startups are popping up, dedicated to making DNA data storage a commercial reality. They are pioneering new synthesis techniques and building end-to-end systems that could one day be as simple to use as today's cloud storage services. We're standing at the dawn of a new information age, one where we're not limited by silicon and magnetic tape, but empowered by the very molecule that makes us who we are. By learning from nature's 3.5 billion year experiment in information storage, we can build a more sustainable, durable, and compact future for our data. The journey from digital bits to biological building blocks is a testament to human ingenuity. It's a reminder that sometimes the most revolutionary solutions are found not in creating something entirely new, but in understanding and harnessing the elegant systems that have existed all along. The data of tomorrow might just be written in the language of life itself. Thanks for watching. What do you think is the most exciting possibility for DNA data storage? Let me know in the comments below. And if you enjoyed this glimpse into the future of technology, don't forget to like this video and subscribe for more content. See you in the next one.